students, Miss DeLeo here, and today we're going to be going over section 3.2 notes on linear versus non-linear functions. All right, so just a little recap is last lesson we learned about functions, and we remember that every x value has a unique y value, or every input has one unique output. That is what makes a relation a function. And now we want to take it a step further and say, okay, well, we have certain types of relations, which are functions, and we have certain types of functions, which are either linear or non-linear functions. In today's lesson, we're going to learn a couple ways about how to identify linear or non-linear functions. So we're going to be able to identify them using a graph. We're going to be able to identify linear or nonlinear functions using a table. And lastly, we're going to be able to just look at an equation and determine if the function is linear or nonlinear. So, one thing that we need to know is that when we're talking about a function being linear or nonlinear, we've already established it is a function. Every x value has one y value. So at least we've gotten that far, and now we're just looking at the specifics of that function. So linear equations look like this, and this may be familiar to you from before, to this structure, y equals mx plus b. We've dealt with equations like this before, and now we're just looking at them kind of in a different light, where x is your inputs and y is your output, and m and b are just constants, which are numbers. Okay? So linear functions in the form of an equation look like this, and we know from prior knowledge that we can rearrange equations to look like this form or not, but what matters is that we have the y variable, we have an x variable with no exponents, no square roots, nothing weird happening. We have an x value and a y value in an equation with some constants. All right, so let's continue. A linear function will. So if a function is linear, it will have a graph that looks like a line. Okay. It will change or progress at a constant rate. So if a function is a linear function, it's going to have a graph that looks like a line, and that line will be changing or progressing at a constant rate. A nonlinear function will have a graph that is not a line, not a straight line. Okay, and it will not change at a constant rate. Okay. All right, so let's go ahead and go through some examples. Now, identifying if a function is linear or non-linear on a graph. Okay, you can already tell that this is a function because it does pass that vertical line test. If I were to drag my pencil across the page, I would hit the graph at only one point all along this function. So that's why I know that it already is a function. They told me that. Now I'm just trying to decide, is it linear or nonlinear? And for this one, we can determine this is a linear function because this graph looks like a line. So yes, it's linear. All right, so over here though, when I look at question number 2, I already know it's a function because it was stated, but just to verify, it does pass the vertical line test. There's only one y value for every x value. But if you notice, we have this little turning point right here. That makes it not a straight line. This turning or pivot point, this is not a straight line. So this would be non-linear. Not a straight line. We have a sharp turning point. Okay. So that's how you decide if something is linear or nonlinear with a graph. Okay, what about with a table? Well, up here we said that a linear function will have a graph that looks like a straight line. Okay, that's how we identify with a graph. And it will change or progress at a constant rate. So let's look at that. For the table, we're going to be looking at that rate of change. So what we want to make sure, and we're going to just note that right here, we're going to have a constant rate of change. For a table. What I want to look at is that as the x values progress by 1, are the y values progressing at a constant rate? So to get from 3 to 5, I add 2, and from 5 to 7, I add 2, and from 7 to 9, I also add 2. Each time, whether it's adding, subtracting, it does not matter. As long as I'm progressing by the same rate, we can determine that the function is linear. So is this a linear function? Yes, it's linear. Our outputs and inputs change at a constant rate. Of +2. So if I can see a pattern in the table, for every one x value, I change 2 y values, that's good. That is a constant change, and I can expect this trend to continue. Let's look at number 4. I notice that the x values are changing by 1. So for every x value, I'm progressing by 1. And for every y value, I've got to find out the pattern. All right, from 16 to 8, I am subtracting 8. And from 8 to 4, I'm subtracting 4. And from 4 to 2, I'm subtracting 2. Okay, this is not a constant rate of change. This is getting smaller each time, which would not indicate a constant rate. One thing that you want to know, and you may be looking at, is that that rate that we're looking for can only be determined by addition and subtraction. That's the constant rate we're looking for. So if you're saying, well, Ms. DeLeo, I see that if we could divide by 2 each time to get 16 to 18, 8, 8 divided by 2 is 4, and 4 divided by 2 is 2. That is not linear. In order to determine if something is linear, they change at a constant rate, and that change is done by either addition or subtraction. So just something we want to make note of. So down here for number 4, we can say this is nonlinear. Our outputs are not changing at a constant rate. All right, so now we've learned how to determine if a function is linear off a graph, off a table, and now an equation. So remember, the structure for a linear equation is that y equals mx plus b form. And so we're looking to see if these 3 problems have that form. All right, so in this equation, we can say, yes, this does have that y equals mx plus b form. We've got y equals, there's my output and my input. And then I've got a constant, and remember, an imaginary constant of, not imaginary, an invisible constant of 1. We don't write 1x because we're too lazy, but we know it's there. So is this linear or nonlinear? Yes. This is linear. Our equation is in y equals mx plus b form. Okay, let's look at the next one. Y equals 3x over 5. If you think back, we really could write this as y equals 3 over 5x. And since there's no number hanging out here at the end, that's really plus 0. So again, I have an output, I have an input, and I have, 2 constants. So we can use our knowledge about solving equations to help us kind of move things around so that it looks like that y equals mx plus b form that we're looking for. And we'll work with this a little bit further, but we have not forgotten what we know about linear equations and about solving equations, and we can definitely manipulate and move things around so that they look like this form. And we can do that by trying to get y by itself if we can't tell. So is this linear? Yes, this is linear. We've got an equation in y equals mx plus b form. All right, for number 7, this kind of looks like y equals mx plus b form. I've got an output, and I have an input, but I realize this input is being squared. That is not a characteristic of something that is linear. Something that is linear is not going to have an exponent connected to its input or its output, okay? So because I have an exponent connected to that input, I know that this is not linear. It is not of that y equals mx plus b form because of that exponent. It's actually an exponential, some type of exponential graph. So not linear, exponent on input is not that y equals mx plus b form we're looking for. So just to go over what we learned today, we recalled what a linear equation looks like. It's in y equals mx plus b form. And of course, we could see that kind of moved around a little bit based off of what we already know about solving equations, but some characteristics are an input, an output, and no exponents or roots or anything like that. A linear function is a graph that looks like a line and it progresses at a constant rate. So for a graph, progressing at a constant rate, no sharp turns, no curves. For a table, we are looking for a constant rate of change, specifically in those outputs. For every one x value, there should be a constant change in y values. And of course, we talked about the equations again. They need to be in y equals mx plus b form. So in class together, we'll do some examples and go over this further. And I hope you guys have a wonderful day.